Welcome! In this session, we will explore the problem maximum product subarray, a popular coding challenge that tests your ability to work with arrays and dynamic programming concepts. Let's dive in and uncover the best strategies to solve this problem. In this problem, you are given an integer array called nums, and your task is to find the contiguous subarray that has the largest product. A subarray is a sequence of elements that are next to each other within the array, and it must contain at least one number. Once you find the subarray with the largest product, you return that product as the result. For the input format, you'll be provided with an integer array, nums, where each element is denoted by nums, I. The output will be a single integer that represents the maximum product of a contiguous subarray. Let's start with an example to make this clear. Suppose the input array is nums equals 2, 3, minus 2, 4. For this input, the output is 6. This is because the subarray 2, 3 produces the largest product. Multiplying the elements of this subarray gives us 2 asterisk 3 equals 6. Now, consider another example where nums equals -2, 0, minus 1. In this case, the output is 0. Why? Because the subarray 0 yields the maximum product of 0. Although the subarray -2, minus 1 has a product of 2, it is not the largest product when considering contiguous subarrays that include 0. This demonstrates how zeros can affect the product calculation and must be carefully considered. Let's look at one more example. If the input array is nums equals -2, 3, minus 4, the output is 24. The entire array, -2, 3, minus 4, forms the subarray with the largest product. Multiplying these elements gives -2, asterisk 3 asterisk, minus 4 equals 24. Now, there are constraints on the input. The length of the array, nums, will range from 1 to 20,000. Each element in the array will have a value between -10 and 10. Additionally, there are edge cases to consider. For instance, if the array contains just one element, the result is simply the value of that element. For example, if nums equals 5, the output is 5. Another edge case involves arrays with all negative numbers. When the array contains only negative values, the largest product will be the product of the largest even-length subarray or the least negative single number. For example, if nums equals -2, minus 3, minus 4, the output is 12, which comes from the subarray -2, minus 3. If the array contains zeros, the product chain is broken at those points. In such cases, the maximum product must be evaluated separately for each segment divided by zeros. For instance, in nums equals -2, 0, minus 1, the output is 0. Finally, when the array has a mix of positive and negative numbers, the product of two negatives can become positive, so it is important to consider such possibilities. As an example, if nums equals -1, 2, minus 3, 4, the output is 24, which is achieved by multiplying the subarray -1, 2, minus 3, 4. Understanding these cases will help you approach the problem effectively. To solve the maximum product subarray problem, we start by considering a few approaches. The most straightforward method is the brute force approach. Here, the idea is to examine every possible subarray, calculate its product, and keep track of the largest product we find. While this method is simple to implement, it involves using nested loops to iterate over all subarrays and computing the product for each, leading to a time complexity of n cubed. This makes it impractical for larger arrays because the computation grows very quickly as the size of the input increases. On the other hand, we also have a more sophisticated method using dynamic programming. Instead of examining all subarrays directly, we focus on tracking the maximum and minimum products at each index. This is important because multiplying by a negative number can flip the sign of the product, so the smallest negative product could become the largest positive product. By leveraging this insight, we can maintain a running maximum and minimum product for each index, which drastically reduces the computational effort compared to brute force methods. In the dynamic programming approach, we maintain two values for each index, the maximum product and the minimum product ending at that index. These are referred to as max_product and min_product. The reason for tracking both is that a negative number can flip the sign of the product, making the smallest negative product potentially the largest when multiplied by another negative number. To implement this, we iterate through the array, updating the max_product and min_product values at each step based on the current number and the results from the previous index. Simultaneously, we keep track of the global maximum product we have encountered so far. This approach brings the time complexity down to O(n), because we only make a single pass through the array. However, it does require additional space to store the max_product and min_product arrays, which introduces an O(n) space complexity. To address this, we can optimize further by eliminating the need for these arrays and using just two variables to store the current maximum and minimum products. The optimized space approach builds on the dynamic programming strategy but reduces space usage significantly. Instead of maintaining arrays for max_product and min_product, we use two variables to store the current maximum and minimum products at any given step, current_max and current_min. We also keep a global_max to track the largest product encountered so far. The process begins by initializing all three variables to the first element of the array. As we traverse the array, we update current_max and current_min based on the current number, swapping them when the current number is negative. This ensures that we correctly account for sign flips. The global_max is updated whenever a new maximum product is found. This method retains the O(n) time complexity of the dynamic programming approach but reduces space complexity to O(1), making it both efficient and memory friendly. The key insight here is that by dynamically updating these two variables, we can achieve the same results without the overhead of additional storage. The optimized space approach stands out as the most efficient and practical solution for this problem. The brute force method is computationally prohibitive with an O(n)³ time complexity, making it unsuitable for large inputs. The dynamic programming approach with arrays improves the time complexity to O(n), but at the cost of additional space for storing intermediate results. The optimized space solution achieves the same linear time complexity but reduces space usage to O(1) by replacing arrays with two variables. This balance of simplicity, efficiency, and scalability makes it the ideal choice. By focusing on the critical insight that the maximum product depends on both the largest positive product and the smallest negative product, this approach effectively handles the challenges posed by sign flips in the array. Overall, the optimized space approach provides a clean, efficient, and scalable way to solve the maximum product subarray problem. The maximum product subarray problem asks us to find the contiguous subarray within a given array that has the largest product. For instance, in the array nums equals 2, 3, minus 2, 4, the subarray 2, 3 produces the maximum product, which is 6. To solve this problem efficiently, we use a dynamic programming approach similar to Cadon's algorithm. The key idea is to track both the maximum and minimum products at every step, as the minimum can become the maximum when multiplied by a negative number. To begin, we initialize three variables, max_product to store the overall maximum product, current_max to keep track of the maximum product at the current position, and current_min to track the minimum product at the current position. All three are initialized to the first element of the array, nums, 0. This setup ensures that we have a baseline to start evaluating the product values as we process the array. Now, we iterate through the array starting from the second element, nums, 1. At each step, we calculate three potential values: the product of the current element with current_max, the product of the current element with current_min, and the current element itself. These three values represent extending the subarray with the current element, accounting for the inversion caused by a negative number, or starting a new subarray. Once these values are computed, we update current_max to the maximum of these three and current_min to the minimum. This ensures that we correctly track both the highest and lowest products at this step. We also update max_product to make sure it always holds the highest product encountered throughout the iteration. Finally, after completing the loop, we return max_product, which contains the result. There are a few key insights that make this algorithm work effectively. First, handling negative numbers is crucial because multiplying two negative numbers results in a positive number, which is why we track both the maximum and minimum products. This ensures we don't miss opportunities to flip a negative into a positive. Second, if the current element is larger than any product involving previous elements, it's better to start a new subarray. This decision is made by directly comparing the current element with the computed products. Lastly, this problem exhibits optimal substructure, meaning the solution at each step builds on solutions to smaller subproblems. From a space and time complexity perspective, this algorithm is highly efficient. It operates in O(n) time since we process each element once, and it uses O(1) space as we only maintain 3 variables throughout the process. To understand how the algorithm handles special situations, consider these edge cases. For a single element array, the result is simply the element itself. When the array contains all negative numbers, the maximum product could either be a single negative number or the product of an even count of negatives, as this would result in a positive product. Arrays with zeros require extra care because zeros reset the product, forcing us to start new subarrays after each zero. Let's walk through an example using nums equals 2, 3, minus 2, 4. Initially, max_product, current_max, and current_min are all set to 2. At the second element, 3, the maximum becomes 6 by extending the subarray, and the minimum becomes 3. The maximum product so far is updated to 6. At the third element, minus 2, the maximum flips to minus 2, and the minimum becomes minus 12 due to the inversion caused by the negative number. The maximum product remains 6. Finally, at the fourth element, 4, the maximum becomes 4 and the minimum drops to minus 48. The maximum product encountered so far remains 6, as extending the subarray doesn't surpass the product we've already tracked. After completing the iteration, the algorithm returns max_product, which is 6 for this example. This step-by-step process demonstrates how the algorithm efficiently handles a mix of positive, negative, and zero values in the array while maintaining optimal time and space complexity. By carefully updating current_max, current_min, and max_product at each step, we ensure that the solution is both accurate and efficient. The provided solution efficiently calculates the maximum product subarray using a dynamic programming approach. The core idea is to maintain 2 running variables, current_max and current_min, which track the maximum and minimum product ending at the current position. This is important because multiplying a negative number can flip the sign, making the minimum product potentially the largest. First, the code initializes 3 variables, max_product, to store the global maximum product, current_max, and current_min, all set to the first element of the input array nums. These variables will help in tracking the maximum product dynamically as we iterate through the array. The loop begins from the second element of the array and processes each number in nums. If the current number is negative, the variables current_max and current_min are swapped. This ensures that the smallest product, which might be a negative value, is correctly used to calculate the maximum product when multiplied with the current negative number. After handling the sign flip, current_max is updated to be the maximum value between the current number alone or the product of the current number and the previous current_max. Similarly, current_min is updated to track the smallest product ending at this position. At each step, the global max_product is updated to ensure it always holds the maximum product found so far. Finally, after the loop completes, max_product contains the result, which is returned as the output. This approach runs in O(n) time as it processes each element of the array exactly once and uses O(1) space, making it highly efficient. It also handles all edge cases, including arrays with negative numbers, zeros, and arrays of size 1, ensuring correctness in all scenarios. Here, we begin with the definition of our solution in Java. The method maxProduct takes an integer array nums as input and returns the maximum product of a contiguous subarray. First, we handle edge cases by checking if the input array is null or empty. If it is, we directly return 0. Next, we initialize 3 important variables, maxProduct, currentMax, and currentMin. The maxProduct variable stores the global maximum product found so far, while currentMax and currentMin track the maximum and minimum products ending at the current position in the array. The inclusion of currentMin is crucial because a negative number can flip the sign of a product, potentially turning a small negative product into a large positive one. After the initialization, we loop through the array starting from the second element. For each element, we first check if the current number is negative. If it is, we swap current max and current min to account for the sign change that would occur when multiplying by a negative number. This ensures that the calculations for the maximum and minimum products remain accurate. Now, we calculate the running maximum and minimum for the current position. The current max is updated as the maximum of the current number itself or the product of the current number and the previous current max. Similarly, current min is updated as the minimum of the current number or the product of the current number and the previous current min. These updates ensure that we account for both the possibility of extending the subarray or starting a new subarray at the current position. After updating these values, we compare current max with max product and update max product if current max is greater, ensuring that max product always holds the global maximum product found so far. Finally, once the loop completes, we return max product as the result. This approach ensures an optimal solution with a time complexity of O(n), as we iterate through the array just once while maintaining constant space for the variables. Here we're starting with the array 2, 3, -2, 4, and calculating the maximum product of any contiguous subarray step by step. First, we initialize three variables, max_product, which keeps track of the global maximum product and starts at 2, the first element, current_max, which represents the maximum product ending at the current position, also initialized to 2, and current_min, which tracks the minimum product ending at the current position, also starting at 2. Now, for nums, 1, which is 3, since it's a positive number, there's no need to swap current_max and current_min. We update current_max to the larger of 3 or 2 multiplied by 3, which gives 6. Similarly, current_min is updated to the smaller of 3 or 2 times 3, resulting in 3. Finally, we update max_product to the maximum of the current max_product and current_max, resulting in 6. Moving to nums, 2, which is -2, a negative number, we swap current_max and current_min, so current_max becomes 3 and current_min becomes 6. Now, updating current_max, we take the maximum of -2 or 3 times -2, which is -2, and for current_min, the minimum of -2 or 6 times -2, resulting in -12. The global max_product remains 6 as -2 is smaller than 6. Next, we process nums, 3, which is 4. Since it's a positive number, there's no need to swap current_max and current_min. We update current_max to the larger of 4 or -2 multiplied by 4, which gives 4, and current_min to the smaller of 4 or -12 times 4, resulting in -48. The global max_product is then updated to the maximum of the current max_product and current_max, and it remains 6. This concludes our calculations for the first example, and the maximum product subarray is 6. Now, for example 2 with the array, -2, 0, -1, we start with an initial max_product of -2, current_max is -2, and current_min also is -2. Moving to nums, 1, which is 0, we treat it as a positive number, so no swapping is needed. Updating current_max, we take the larger of 0 or -2 multiplied by 0, which results in 0. Similarly, current_min becomes the smaller of 0 or -2 times 0, which is also 0. The global max_product is updated to the maximum of -2 and 0, giving us 0. Now, for nums, 2, which is -1, a negative number, we swap current_max and current_min. Both were 0, so the values remain unchanged. Updating current_max, we calculate the larger of -1 or 0 multiplied by -1, which gives 0. For current_min, we take the smaller of -1 or 0 times -1, resulting in -1. The global max_product remains 0, as neither current_max nor current_min exceeds it. This completes the calculations for example 2, where the maximum product subarray is 0. Moving on to example 3, with the array, -2, 3, -4, we begin by initializing max_product to -2, current_max is -2, and current_min also is -2. For nums, 1, which is 3, a positive number, no swapping is needed. Updating current_max, we take the larger of 3 or -2 multiplied by 3, giving 3. Similarly, current_min is updated to the smaller of 3 or -2 times 3, resulting in -6. The global max_product is updated to the maximum of -2 and 3, which gives 3. Now for nums, 2, which is -4, a negative number, we swap current_max and current_min. After the swap, current_max becomes -6, and current_min becomes 3. Updating current_max, we calculate the larger of -4 or -6 multiplied by -4, resulting in 24. For current_min, we take the smaller of -4 or 3 times -4, which gives -12. Finally, the global max_product is updated to the maximum of 3 and 24, giving us 24. This concludes the calculations for the third example, and the maximum product subarray is 24. By following this approach, we can systematically determine the maximum product for any given array, using dynamic updates to track the current maximum and minimum products as we iterate through the array. The time complexity of this algorithm is O(n), where n is the number of elements in the input array, nums. This efficiency comes from the fact that the algorithm requires just one pass through the array. Starting from index 1, the loop processes each element exactly once, performing a series of constant time operations for each iteration. These include checking if the current number is negative, possibly swapping current_max and current_min, and computing the new values for these variables using the max and min functions. Additionally, the algorithm updates the global max_product, all of which are O(1) operations. Since these constant time operations are performed n times, once for each element, the total time complexity is O(n). Importantly, this holds true whether the input array is randomly distributed, sorted, or contains all negative numbers, since the loop always iterates through every element. The space complexity of this algorithm is O(1), as it uses a constant amount of extra memory regardless of the size of the input array. Specifically, the algorithm requires 3 variables, max_product, which keeps track of the global maximum product, current_max, which represents the maximum product at the current position, and current_min, which tracks the minimum product at the current position. Each of these variables occupies a fixed amount of memory. Additionally, no auxiliary data structures, such as extra arrays or stacks, are used. The input array nums is processed in place without modification, further ensuring that the memory usage does not grow with the size of the input. Therefore, the space complexity remains constant at O(1). Comparing this optimized approach to a brute force solution highlights its efficiency. In a brute force approach, we would calculate the product of every possible subarray. This involves generating all subarrays, which results in O(n²) combinations, and then calculating the product for each subarray, which adds another O(n) operation. Altogether, this leads to a total time complexity of O(n³). In contrast, the optimized approach avoids these redundant calculations by using dynamic programming principles to maintain running values for the maximum and minimum products at each position. This reduces the time complexity from O(n³ to O(n), while still requiring only O(1) space for a few variables. This makes the optimized approach far more scalable and practical for larger input sizes. The mathematical reasoning behind the algorithm's big O complexity further illustrates its efficiency. Each element in the array is processed exactly once, resulting in O(n) iterations. During each iteration, operations such as multiplication, comparison, and swapping are performed, all of which are constant time operations with a fixed cost. Because these operations do not depend on the size of the input, their complexity is O(1). Combining these factors, the overall time complexity of the algorithm is O(n). Similarly, the space complexity remains O(1) due to the use of only a fixed number of variables. In conclusion, the optimized approach is highly efficient, achieving both linear time complexity and constant space complexity. Compared to the brute force solution, this represents a dramatic improvement, making the algorithm well-suited for processing large arrays efficiently. One common mistake to avoid when solving the maximum product subarray problem is resetting the product whenever you encounter a 0. It might seem intuitive to treat 0 as the end of a valid subarray, but this approach can cause you to miss potential maximum products. Instead, you should treat 0 as a boundary, evaluating the product on either side and continuing the traversal. Another frequent error is ignoring negative numbers entirely. While negatives might seem problematic, they can actually help maximize the product if there's an even number of them in the subarray. This is why it's important to keep track of both the maximum and minimum products as you iterate. Additionally, failing to handle edge cases, like arrays with a single element, can lead to incorrect results. For example, in a single element array, the maximum product is simply the element itself. Lastly, avoid using floating point operations unnecessarily if the input contains integers. Integer arithmetic is faster and prevents subtle rounding errors, so stick to it unless the problem explicitly requires floating point values. Overcomplicating the algorithm is another pitfall to watch out for. Some solutions attempt to split the array multiple times or use extra space unnecessarily, but the optimal solution is much simpler. By maintaining just two variables for the current maximum and minimum products, you can solve this problem in O(n) time with O(1) space. Now, in an interview setting, there are a few key points to emphasize. First, always track both the maximum and minimum products at each index, since multiplying by a negative number can flip the sign and dramatically change the result. You should also be ready to compare approaches. While a brute force O(n)² solution might work, it's important to articulate why the dynamic programming-inspired O(n) approach is superior. When discussing edge cases like zeros, negative numbers, or single-element arrays, make sure to highlight how your solution handles them. This demonstrates thoroughness and a deep understanding of the problem. Finally, optimal space usage is another strong point to bring up, as the most efficient solution only requires a constant amount of extra space. This problem also ties closely to several related challenges that you might encounter. For instance, maximum subarray, also known as Cadon's algorithm, is a classic problem where you track the maximum sum of contiguous subarrays instead of products. Another variation, subarray product less than k, focuses on counting subarrays with a product constraint, requiring a slightly different approach. Then there's the longest subarray with product positive, which emphasizes maintaining positive products throughout traversal. While the exact details differ, the logic of managing products and signs remains relevant. Finally, the contiguous array problem, though tackling a different goal, uses similar prefix tracking techniques to solve it efficiently. Exploring these related problems can help reinforce the concepts and make you more adaptable in solving variations in interviews. There are also alternative approaches to solving the maximum product subarray problem, each with its own trade-offs. The brute force approach, for example, involves checking every possible subarray to find the maximum product. While this is simple to implement, its O(n)² time complexity makes it impractical for large arrays. Then there's the dynamic programming approach, which uses additional arrays to store intermediate results. This method simplifies the logic but increases space complexity to O(n), making it less efficient than the optimized solution. The most efficient approach involves a single sweep of the array while maintaining two variables for the current maximum and minimum products. This technique achieves O(n) time and O(1) space complexity, but it requires careful handling of edge cases, such as zeros and negative numbers, which can be tricky for beginners. Understanding these trade-offs not only helps you choose the best solution but also prepares you to explain your choices in an interview setting. Great job! To summarize, we've tackled the maximum product subarray problem using efficient techniques that balance time and space complexity. Remember to practice handling edge cases like negative numbers and zeros. Stay tuned for more coding challenges, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!